So, good morning, students. So, last class we have discussed about memory address decoding. So, the decoding can be done by using three techniques. That is, one is about using logic gates, and second one is about using 74LS138 decoder, and third one is using programmable logics. Okay. So in this class, we are going to see about how to interface 8031, that is 8031 microcontroller with external ROM. Okay. So basically, 8031 IC, it is an interversion. So this IC is a ROM-less version of 8051. So the particular microcontroller does not have internal ROM. Okay. So remaining architectures are very similar to your 8051. That is, all your instruction set and architectural components are very similar to 8051. So it's exactly like any member of 8051 family as far as executing the instructions and features are concerned. So the architecture is very similar to 8051, but the only difference, it doesn't have internal ROM memory. So we have to connect external memory for this particular microcontroller, and also it must be connected to external ROM memory containing your program code. Okay. And second important thing is to make 8031 executes your 8051 code, it must be connected to external ROM memory containing program code. And most of the applications, this 8031 is ideal. Okay, many real-time applications, this 8031 is it's ideal, that is widely used, where on-chip ROM of 8051 is not sufficient. Since 8051 has only 4 KB flash memory, so that is not sufficient for real-time applications. So 8031 is widely used for many real-time applications because it allows the program size to be as large as 64 kilobytes. So we can connect 64 kilobytes of memory with your 8031 microcontroller. And another important point is, so comparing to your 8051, the 8031 chip is much cheaper than other microcontroller family. And also the 8031 based system is much more expensive since the ROM containing the program code which is connected externally and requires more supporting circuits. So that is the drawback of this particular IC, 8031 IC. Okay. So we will see about some of the important details, important pin details to interface external memory with your 8031 microcontroller. So the first pin is EA pin. Second one is P0 and P2. So these pins are required to interface your external memory with 8031 microcontroller. And third one is about ALE pin. Fourth one is about program store enable pin. So we will see one by one. So EA pin, what is the purpose of EA pin? I have explained this EA pin details in 8051 architecture. So what is the purpose of EA? So what is the purpose of EA pin? So when EA is connected to VCC, what will happen? When EA is connected to ground, what will happen? Can anyone answer? So these pin details I have explained in 8051 architecture. Okay. What is EA? What is the expansion of EA? To access external memory when it is low. Okay. Suppose when it is connected to VCC, what will happen? It will access internal memory. Okay. So EA is connected to VCC to indicate that the program code is stored in the microcontroller on chip ROM. That is the meaning. Okay. To indicate that the program code is stored in the microcontroller on chip ROM. Suppose if your EA is connected to ground means to indicate that the program code is stored in external ROM. So using this EA pin, microcontroller will understand whether the code is found internally or externally. Okay. So that is the purpose of EA pin. Is that clear? Students, is that clear? So in this case, 8031, the EA should be connected to ground or VCC. Can you understand my question? In case of your 8031 microcontroller, it is a ROMless microcontroller. In that case, EA should be connected to ground or VCC. So what is the answer for that question? So can anyone answer? Ground. Why it is ground? Why it is grounded? ROMless. ROMless means doesn't have internal ROM. Memoryless IC chip. We have to connect external memory for that particular chip. Your 8031 is a ROMless IC microcontroller. So it has no on-chip ROM. That is the meaning. Is that clear, Balameenakshi? It has no on-chip ROM. In case of 8051, we have 4 KB on-chip ROM. So that is the difference between your 8031 and 8051. Okay. So EA is playing a major role to distinguish between your external and internal memory. Suppose if EA is connected to ground means your code is found externally. Your microcontroller will understand that the code is stored externally. Okay. Suppose if it is connected to VCC to indicate that the program code is stored in internal memory. So that internal memory case is not possible in case of 8031 microcontroller. So we have to connect the external memory. Okay. And also the EA must be grounded. Okay. So this is the IC pin diagram of your 8031. So the pin details are very similar to, more or less very similar to your 8051. Not much difference. So we have P1, P0, P2, okay, and external oscillator circuitry and port 3 and program store enable, EA and address latch. The only difference, it has no internal on-chip ROM. And what is the purpose of P0 and P2 in providing address? So what is the role of P0 and P2? Do you have any idea about it? While interfacing external memories. So what is the role of P0 while accessing external memory? You should answer. So these topics were already covered in your first unit. So actually here your 8031 is capable of accessing up to 64 kilobytes of program code. So which means that we can connect 64 KB external ROM chip with 8031 or 8051 microcontroller. Okay. So your program counter size is 16-bit. Okay. So it is capable of accessing up to 64 kilobytes of program code. That is 2 power of 16 means it is capable of accessing up to 64 kilobytes of program code. In 8031 and 51, your port 0 and port 2 provide 16-bit address to access external memory. They are demultiplexed with address bus used for data and S. Yes, Balameenakshi. Manishri, it's a correct answer. Okay. So P0 and P2 will provide the 16-bit address to access external memory. So lower address will be provided by your P0 and higher address will be provided by your P2. So P0 will hold lower 8-bit address and P2 will hold upper 8-bit address. In that case, P0 case, the address and data are multiplexed. AD0 to AD7. Okay, so P0 is used for both address and data path. So that is called address and data multiplexing. So P0 provides lower 8-bit address and P2 provides upper 8-bit address, and also your P0 can be configured as a 8-bit data bus. So used for both an address data path. Okay. So my question is here, how do we know when P0 is used for data path and when it is used for address path? That is my question. You have to answer. So single port can be utilized for handling both your address and data. How is it possible? How do we know when P0 is used for the data path and when it is used for address path? Using ALE, very good. So address latch enable. So address latch enable is the output pin of 80, 31 or 51. So when ALE is equal to 0 means P0 is used for address path. When ALE is equal to 1 means P0 is used for address path. Okay. So to extract the address from P0 pins, we have to use this decoder 74LS373. Okay. So it's a D-latch circuit. So this circuit is used to demultiplex the address and data lines. Okay. So to extract the address from P0 pins, we have to connect P0 to 74LS373 and use ALE pin to latch address. Please look at this diagram. So here the address lines are one by one connected to the latch. Okay. When ALE is an ALE is connected to the D latch, that is 74LS 373, and here we have A0 to A7 and here we have D0 to D7. So this circuit is used to demultiplex this multiplexed address and data line. Okay. So this can be demultiplexed by using this ALE signal, address latch enable signal. When ALE is equal to 0 means for P0 is used as address, sorry, data bus. So ALE is equal to so your P0 is used as data bus, sending data out and bringing data in. So that is the purpose of data bus. So it's a bidirectional. Okay, whenever the 80, 31 or 51 wants to use P0 as an address bus, it put the address A0 to A7 on the P0 pins and activates ALE is equal to 1. So ALE is used to demultiplex the address and data lines. When ALE is equal to 0 means P0 is used as data bus. Otherwise, it is used for address path. So this is the internal structure of this D latch. Okay. So here 8 port pins are connected. We have 8 inputs and it can generate 8 outputs. So based on this function table, it will work. Okay. So the output will be high or low or reverse Q bar or high impedance. So based on the input, that is your G and D, your output will be in high state, low state, or reverse state, that is complement state, or in high impedance state. So next thing is program store enable. What is program store enable? It is also a output signal. So this signal must be connected to the output enable pin of your external ROM which is containing program code. So EA pin is connected to ground. 8031 fetches the opcode from external ROM by using this program store enable. Okay. So when the external ROM memory is connected means 8051 or 8031 can fetch the opcodes or instruction bytes from external memory by using program store enable. Suppose if EA is connected to VCC means your program store enable is never activated because your on-chip ROM contains program code. So when EA is equal to ground means your program store enabled should be activated to access the instruction bytes available in your external ROM. So that is the purpose of program store enabled. So this is the block diagram here. Suppose when the external memory is connected means, so you have to think of read bar, write bar. So this read bar should be connected to your external ROM memory and program store enable for accessing data bytes from external memory. And P2 can be used for address path. It can hold higher order address information, and your P0 can hold lower order address information. Similarly, it can be configured as data bus. Okay. So these are the important pins connected with your 8031 with external memory. Here EA should be grounded and program store enable should be connected to the output enable of your external ROM. So this is the complete connection of 8031 microcontroller with external program memory, ROM memory. So the size is 8K cross 8 program memory. Here you can see your program store enable is connected to output enable pin and also chip enable pin to access instruction bytes from program ROM. Okay. So here A8 to A12 are directly connected to the address pins of your memory, and A0 to A7, that is your P0 is connected to the A0 to A7 pins of your program memory, and A13 and A14 and A15 may be used for address decoding. So these three address lines can be utilized for address decoding to select the memory blocks. And EA should be grounded. So these are the connection details of interfacing your 8031 microcontroller with external program ROM. Okay. So next, coming into on-chip and off-chip code ROM, in 89C51 is similar to your 8051 microcontroller. So here we can use on-chip ROM for boot code. So booting initialization should be stored in on-chip ROM, and external ROM will contain user program. Okay, so that case EA is equal to VCC. So upon reset, your 8051 execute on-chip program first. Then when it reaches the end of your on-chip program, it switches to external ROM for the rest of the program. Okay. So in 8051 follows this type of structure while interfacing your external memory. The 4K is completely utilized for storing your boot code, and your external memory will be utilized for storing your user program. So in that case, your EA should be connected to VCC. So upon reset, your 8051, first it will execute on-chip program. That is, it will execute boot code for initializing all your peripheral devices. When it reaches the end of the code, it automatically switches to the external ROM for executing the rest of the program. Okay. So here, this diagram clearly explains about your on-chip and off-chip program code access. In case of 80, 31 and 51 microcontroller, EA must be grounded. Here, the code will be available with the off-chip ROM, that is external memory, that is 64 KB. The size is 64 KB. So the address range from 00 to 4F. In case of 8051, we have internal memory, that is on-chip memory. The size is 4K, address range 0000 to 0FFF. And also we will have off-chip memory, external memory, and the address range is from 1000 to FFF. So this can be utilized for storing your boot code, and this can be utilized for storing your user program. And in case of 8052, EA is connected to VCC, and here we have on-chip ROM, the size of 8 KB. So the address range 00 to 1FF. Off-chip we have separate memory from 200 to address range to FFF. So this is the difference between your on-chip and off-chip program code access based on your different microcontroller architecture. In 8031 microcontroller, it has no internal memory. We have to store our program code externally. In case of 8051, it is divided into internal memory and external memory. And internal memory will be utilized for storing your booting initialization code, and external memory will be utilized for your user. The same structure will be followed for 8052 microcontroller, but on chip we have 8 KB memory. So far in all our discussions about memory space has involved program code. So next we will discuss about the data memory space. So in case of 8051, the program counter size is 16-bit. So it is capable of accessing up to 60 kilobyte of program code. So next we will see how to get the data from the code space, and also the capacity of the data space in 8051 microcontroller. And also we will see what are the instructions involved to get the data from the data space and also program space. Okay. So in 8051 has 128 kilobytes of address space. Okay. So complete the address space is 128K. So this 128K is divided into 64K and 64K. So the first 64 kilobytes are utilized for storing program code. Okay. And other 64 bytes are utilized for storing your data. Okay. So here to access data in the program code, we have to use this instruction movc a comma at a plus dptr to get data. Okay, where C stands for core. It representing your core memory. Okay, so your program space is accessed by using program counter to locate and fetch instruction in case of your program code. Okay, please listen carefully. You have to understand the difference between your program code and data code. Okay, data space. Okay, next data space is accessed using dptr register. Here we have to use move X instruction. X represents external memory. Okay. So in case of your program code, to access your data bytes, you have to use move C instruction. In case of data memory space, we have to use move X instruction. Okay. So please look at the connection details of this diagram. So this is data ROM, not program ROM. So can you understand the difference between program ROM and data ROM? So what is the difference? Please tell me. Just you observe this diagram. So what do you infer from this diagram? Please tell me. Please tell me. So it's a 8051 data memory space. What are the signals are involved? So what about your EA and what about your program store enable? What type of decoding circuit is used here to generate chip select signal? Yes, Balaminakshi, program store enable is not connected. Why it is not connected? What is the reason? So here program store enable is ignored. What is the reason? So to connect the 8031 or 51 to external ROM containing data space, we have to use read pin, that is pin number 3.7. Okay. Suppose if the ROM is containing program code, means program store enable is used to fetch the code. So here only data is involved. So your program store enable is not activated. You have to connect P3.7 to output enable pin of your data ROM. Okay. Is that clear, students? So here, please look at the connection. Your P3.7 is the read signal. Okay, so that is connected to the output enable of your data ROM. So you must understand the difference between your program ROM and data ROM. Suppose if program ROM is connected with your microcontroller, that case we have to use this program store enable, and your EA must be grounded for that case. Okay. So for ROM containing program code means the program store enable is used to fetch the code. Okay. So can you find out the address range for this particular IC using this decoding circuitry? Here A15 and A14 and A13 are utilized for identifying your address range. Okay. So here they have used logic gate decoding, memory decoding circuitry. So please find out the address range for this particular architecture. So A15, A14 and A13 are inverted. So how it is E00? 0, 0, 0, 0, all zeros, no? Yes, all zeros, not E0. So if it is inverted means your A15 should be 0. 0, 0 to 1 triple F. Okay. So the address range can be decoded by using this circuit. Here your A15 must be 0, 0, 0 in order to generate your chip select signal. So remaining all your A12 to A not all are 0. So your answer is starting address answer is 0, 0, 0, 0. Suppose next case 0, 0, 0. This must be 1. Remaining all the bits are 1. So 1 triple F. So using this circuit, using this interfacing circuit, we can access the address range from 000 to 1 triple F from 8K cross 8 data row. Here your program store enable is not activated because we are accessing data ROM here, not program ROM. Okay. So this slide explains about the difference between your move X instruction and move C instruction. So here move C and move X are very similar, that is look very similar. So your move C is used to get data in code space, that is program space, program memory. Using this instruction, we can access the data elements from program memory. And move X is used to get the data in the data space of the microcontroller. So that is the difference. To bring externally stored data into CPU, we have to use this move X instruction. So look at this example. It is a digital to analog converter example. So already a lookup table will be stored at a memory location 100. That is pre-calculated values are loaded in the memory location starting from 100. Here we have to write a program to read 30 bytes of data and send it to P1. Okay. So your starting address is your my X data. Count will be 30. So first your starting address is loaded into DPTR and count 30 is loaded into R2. Using this instruction, we can access the data from 1000. So this is externally connected. So this memory is externally connected. We can use this instruction to access the data from external ROM memory. So get the data one by one and move the data P1, increment DPTR and decrement the count. So in this way, we can access the data elements from external memory. For that, we have to use MOVEX instruction. Suppose you have to access data from the program code. For that case, you have to use MOVC instruction. So next one is the complete design of your 8031 based system with 8 kilobytes of program memory and 8 kilobytes of data memory. So both the memories are coming into the picture. Just you look at this diagram. So first we will see about this 8K cross 8 data ROM. Please observe the connections. So here, this circuit is used to generate chip select signal, and this output enable is connected to read bar. That is 3.7 is connected to the output enable pin of your data ROM. So data ROM means we have to connect this read bar. Program ROM means we have to connect program store enable. So A15, A14 and A15 is all the address pins, 3 address pins are utilized for generating chip enable signal, and remaining pins are connected to the address pins of your data ROM and program ROM. And this circuit is used to demultiplex your lower order address and data bus. So this diagram clearly explains about the interfacing your external data ROM and program ROM with 8031 based system. Here, look at here, your EA must be grounded. So for program ROM, program store enable is used to activate both output enable and chip enable. For data ROM, we have to use read to activate output enable, while CE is activated by simple decoder circuit. So this diagram is very important in this unit. If you have any doubts regarding connections, you can ask your doubts. Any doubts regarding this? A very important question in this unit. Do you have any doubts? So when data space is involved, you have to connect read bar signal. Program space is involved, you have to connect program store enable. When program store is activated, store enable is activated means EA must be connected. So entire code will be available externally. So that is the concept involved in this 8031 based, 8031 based microcontroller system. Do you have any doubts, students? What about others? Okay. So this is about your data RAM, not ROM. Data RAM, random access memory. Here, in case of data RAM, this program store enable is never activated. Here the connection is to enable read and write, you have to connect this 3.7 to output enable pin of your data RAM, and 3.6 should be connected to the write enable of data RAM. And here we have simple decoder circuit to access the data elements from the memory, and A13 to A8 connected to the P2 connected to the A13 to A12 of address pins of your data RAM. So the only difference, read bar and write bar. So we must use both read and write. 3.7 and 3.6 should be connected to output enable and write enable pin of your data RAM. Okay. So in case of data RAM, when writing data to external data RAM, we have to use instruction, same instruction, move X at dptr, A. Okay. So the meaning is here, move X at dptr, A means where the content of register A is written to external RAM whose address is pointed by dptr. That's all. Same, similar to your data ROM. Okay. So for this data RAM, find out the address range for this circuit. Logic circuit. Find out the address range. So what is the answer? 8002 B triple F. Okay. So the given problem statement is, refer this diagram and write a program to read 200 bytes of data from P1 and save the data in external RAM starting at RAM location 800. So address ranges we have already calculated, 8000 to B triple F. So you have to get the data from P1 and transfer the data into corresponding memory location, RAM memory location starting from 8000. Please do it. So first you have to initialize your DPTR, next initialize your count, and next transfer the data from P1 to accumulator and move the accumulator content to the data that is address pointed by DPTR, increment DPTR and decrement the count. Completed, students? Uday Kumar, completed?
I'm doing, ma'am.
Okay. So based on the interfacing diagram, the address space allocated is from 8000 to B triple F. Okay. So the problem statement here is you have to read 200 bytes of data from P1 and save the data in external RAM memory starting from 8000. So first instruction will be move dptr comma hash 8000. So this will be the starting address of your RAM memory location. Okay. And next, what is the count given here? Count is 200. So move R3 comma hash 200. Either you can give decimal value or hexadecimal value. I am giving decimal value here. Okay. So according to the problem statement, you have to move the data from P1 to your data pointer, because since your data pointer is pointing 8000, so first you move the data available in P1 to accumulator. Okay. Next, use move X instruction, move your accumulator content to DPTR, because now your DPTR is pointing external RAM address, that is 8000. Okay. So for transferring each data, it will take some amount of time. So you can call generate uh, generate some amount of delay by using writing delay routines. And next, increment dptr, decrement, you have to decrement R3 and L1, your program control goes to move A comma P1. So when external RAM is connected, you have to access or you have to store your data in the external RAM, or accessing, that is storing the data elements from microcontroller to your memory. We have to use this move X instruction. So programming can be done by using this method to transfer the data from microcontroller to your external RAM location. Is that clear, ma? Is that clear? We should configure P1. Actually, data will be available in P1, not it is a input port, not accepting the data from P1. Your memory IC, let's assume your external RAM is interfaced with your P1 of your 8051 microcontroller. Here P1 is not as an input port. Your external RAM is reading the data from P1. Okay. So data, all the data, there is 200 bytes of data available in P1 port. We have to read the data from P1 and store the data in the external RAM memory. So there is no need of configuring your P1 as an input port. Any other clarifications? Okay. So this is the answer for this problem. So next problem is here data RAM. Again 16K cross 8 data RAM is interfaced with the 8051 microcontroller. So here write a program to transfer array of 10 bytes stored in location starting from 8000 in this RAM, same location from 8000 to 9000. You have to transfer 10 bytes of memory block starting from 8000 to memory location starting from 9000. Okay. So first you find out the address. So address is 10. A13 to A0 will be 0. So 80. 1 0 to all zeros. So 800 is a starting address. And next 1011 means B triple F. Is that right? Okay. So address spaces we have identified. Only we can access the data elements from 8000 to B triple F. So this is the address limit. So here you have to transfer block of data from 8000 to the starting address of 8000 to the another block starting address 9000. Here you have to use only one data pointer DPTR. Okay. So program store enable is not activated. Your read bar and write bar are connected to write enable and output enable. So here two arrays have to be addressed. One is the source array, other one is the destination array. Source array starting address 8000, destination array starting address 9000. Okay. So only one data pointer is available. So we have to use a DPTR to address both the arrays. So when DPTR is pointing to the first array, the current pointing address of the second array is temporarily stored in registers R1 and R2. So this is the logic for writing this particular interfacing program. So first only one pointer is available. So when DPTR is pointing the first array and temporarily store your second array starting address, the current pointing address into R1 and R2. Likewise, when DPTR is pointing the second array, the current pointing address of the first array is temporarily pushed onto the stack. So this logic should be followed to implement block of transfer from 8000 to 9000. Please do it. It's a very simple program. No, we cannot use port 0 with R0 and R1. So you have to follow this one, TPTR alone, because the external memory is interfaced. See, the logic here is first initialize your count value in general purpose register and make DPTR to point 9000. Okay, and move the current pointing DPTR value into R0 and R1. And next you make DPTR point 8000 memory address. Move that value into A. Is that clear? Increment DPTR. It's pointing 8001. Push that 8001 into into stack pointer. That is your DPL, DPH into stack pointer. And now transferring your R0 and R1 to DPL and DPH. And transfer your accumulated data into DPTR. So the logic is here. First initialize DPTR with destination array starting address. Okay. So move your DPL to R0. Okay. And move DPH into R1. So your 00 will be available in R0 and 90 available in R1. And next, make DPTR to point 8000. Okay. So it's pointing 8000. Next step, you have to access the data from 8000 and move that data to accumulator. So add dptr to accumulator. Is that clear? Okay, now data is available in accumulator. Next, increment dptr, which means it's pointing 8001. And push this value 8001 into stack pointer by using push dpl push dph. Now 8001 value is pushed into stack pointer. Okay, so next one, so now your 9000 will be available in a R0 and R1. Transfer that value into dpl and dph. So now your DPTR is pointing 9000. Okay. Your accumulator holds 8000 data. You have to transfer the data, that is the content of your 8000 into 9000. Okay. So your DPTR is now pointing 9000. Move this accumulator content to DPTR now. Okay. Next, increment DPTR. Again, transfer DPL, DPH into R0, R1. So after this, increment DPTR. That means pointing 9001. Okay. And R0 to DPL. R1 to DPH. Now pop DPL and DPH. Repeat the steps. So first, make DPTR to 0.9000 and move that 9000 into R0 and R1. Okay. And next, make DPTR to 0.8000 and transfer the content of DPTR to accumulator. Now the content of 8000 will be available in accumulator register. Next, increment 8001 and push that value into stack pointer. Now 8001 is pushed into stack pointer. Now what we will do is transfer this R0 R1, that is 9000 value into again DPTR. Now DPTR is pointing 9000. So transfer your accumulator content to DPTR. Now the 8000 content will be transferred to the memory location 9000. Increment DPTR pointing 9001. Again you transfer the DPL content to R0 and R1. You pop up the DPL and DPH. So current your stack pointer, that is currently your stack pointer is holding 8001. And decrement the count 1 because one data transfer is completed. Repeat the step. Okay. Again, you transfer the 8001 content to DPTR, that is accumulator. Increment 8002. Likewise, you have to repeat the same operations. Is that clear, ma? The logic is clear? Yes or no? Okay. So convert this logic into program, assembly level program. So this is your code. Please listen carefully. So here count is initialized in which register? R2 register. Okay. And next According to this instruction, your DPTR is pointing the first address of second array, that is array 2, okay? And save the destination pointer in register R1 and R0. Now your 9000 will be stored in R0 and R1, which means that your R0 holds LSB and R1 holds MSB. So your count will be 10 here, and array 2 9000. So here your R0 holds 00 and R1 holds 90. LSB will be holded by R0 and MSB will be holded by R0. And next DPTR points source array starting address 8000. Next, transferring the content of 8000 into accumulator. Okay. Next, increment accumulator. It's pointing 8001. So the problem statement is from 8000 to 8009 to complete block to 9000, 9009. So after incrementing, you have to push this address into stack pointer. So 8001 is pushed into stack pointer. Again, get the destination address in DPTR because R1 and R0 hold 0090. Now DPTR is pointing 90. Now you transfer the accumulator content to DPTR. So the first data transfer is completed. That is 8000 to 9000 completed. Next, I am incrementing DPTR and transfer the lower byte of destination address in R0 and upper byte of destination address in R1. That is, this one holds 9001 and pop up the value 8001. Again, repeat the same. That is 8001 content is transferred to accumulator, and next pointing 8002. Likewise, you have to transfer the data one by using single pointer DPTR because only one instruction will be available to access data elements from external memory. So we have to use this instruction. So using this instruction, your 8051 only accept only one data pointer, that is DPTR. So the instruction is move X at DPTR, comma A. So using this application, we can transfer the block of elements from one array to the next array within the same IC, same memory chip. So move X instructions can be used for external RAM data accessing. Is that clear? So next class we will see about single external ROM for code and data. So it's a complete, so this block diagram explains both your RAM memory and ROM memory. In ROM we have program and data, okay. So this block diagram completely explains your external RAM and ROM memory. So next class we will discuss about this external, that is 8051, that is single external ROM for code and data. So any other doubts? Students, any other doubts?